This section of the course covers the power management of MIPS cores. Power is a factor of the clock frequency. The lower the frequency, the lower the power. The cores are designed to run down to a zero clock. They can do this because there's a mechanism to wake them up through an external pin interface. I'm going to talk about two methods to control the power consumption of the core. The first will be register controlled. The second will be controlled through the use of the wait instruction. Let's talk about register controlled power management. Your code can decide when to request low power mode by setting the reduced power bit in the coprocessor 0 status register. When the reduced power bit is set, the core will signal the external interface through the system interface reduced power pin. The external interface will determine if it can reduce the clock frequency. When running at a zero clock rate, the system interface interrupt, reset, or non-maskable interrupt pins can still signal the core. The core in turn can signal the external interface through the system interface ERL pin if it detected a reset or non-maskable interrupt, or it can signal an external interface through the system interface EXL pin if it detected an interrupt. The external system interface can then determine if it wants to increase the clock speed to service the event. Your code can send the processor into sleep mode through the use of the wait instruction. The clocks are not stopped until all bus and processor transactions are completed. In this mode, external clocks are suspended and the pipeline is frozen. The code signals the external interface through the system interface sleep pin. Any enabled interrupt, NMI, debug interrupt, or reset condition causes the CPU to exit this mode and resume normal operation. The wait instruction is commonly used by an OS in its idle loop. It would seem simple to use an if statement with one function call that in turn executes the wait instruction, but this can cause a race condition because there is no atomic check of interrupt pending and executing the wait instruction. An interrupt can slip in between the pending check and the call to wait. Your interrupt code will process the interrupt and return to a point that the wait instruction is being called. If the interrupt you just processed was the interrupt you were waiting for, the CPU could wait forever or until the system gets another interrupt. This is not what you want your system to do. I'm going to show you how to avoid waiting forever with a code example. There are two parts to the process. First is an assembler wait function to put the CPU into low power mode. The second is a snippet of code to be used in the beginning of any interrupt function that will check to see if the interrupted code was in the process of calling the wait function. These two parts go hand in hand to form the proper way to use the wait instruction. I'll also talk about a change to our more recent cores that can be used to simplify this approach. For this code to work, the wait function needs to be aligned to a 32-byte boundary, and there must be exactly 8 instructions from the beginning of the function through the wait instruction. This alignment makes it easy to determine the address range of the wait function. We must also use .set no reorder, so the assembler will not rearrange the code or eliminate the no-op instructions we have placed to control the alignment of the code. The first thing the code does is to load the iflags variable using an offset to the global pointer, which is stored in general purpose register 28. You should assume that these flag bits are set by the interrupt routine and used to control the state of the interrupt. Next, it isolates the need reschedule flag. Assume that this flag is set by the interrupt routine after it has processed an event that would unblock a process that was waiting for it. The flag is tested, and if set, the code will branch forward around the wait instruction. If not set, the code will fall through the no-ops and execute the wait instruction. When an event happens that takes the CPU out of low power mode, the function returns. In the interrupt routine, the code checks to see if the interrupt occurred within the wait function by checking the EPC value against the range of the wait function. If the interrupt happened while the wait function was being executed, the address in the EPC will be somewhere in the range of the wait function. First, the code gets the error program counter. Next, it gets the address of the wait function. Since we want to know if the address is within a 32-byte boundary that makes up the 8 instructions of the wait instruction, and we know the wait instruction was aligned to a 32-byte boundary, the code masks off the lower bits of the address. Now it tests to see if the masked address is the address of the wait function. If it finds the EPC is in the range of the wait instruction, the code will overwrite the EPC with the address of the wait function, so the execution will resume at the beginning of the wait function once the interrupt returns. This way, we will always assure that the pending flag, which might be updated by the interrupt routine, will be assessed again before the wait instruction is called. There is a new feature in some of our cores called Wait IE Ignore. Your code can check coprocessor 0 config 7 registers Wait IE Ignore bit WII. This read-only bit will tell you how the core treats interrupts while in the wait state. If the WII bit is set, the wait condition will be terminated if an active interrupt is detected, whether or not interrupts are enabled. Note, the interrupt mask will still apply. This only changes the interrupt enable bit behavior when the core is in the wait state. This allows you to clear the interrupt enable bit before deciding to execute the wait function, thus eliminating the possibility of an interrupt coming between the check of the pending flag and the execution of the wait instruction. There is also no need to check in the interrupt code to see if the interrupt was in the wait function. Here is an example of the simplified code. The status register is read and that value is preserved. The code explicitly clears the interrupt enable bit and moves it back to the status register. Now the code gets and checks the I need reschedule flag, and if it is set, it branches around the wait instruction. If the I need reschedule flag is clear, the wait function is executed. When the wait is interrupted, the status register is restored and the wait loop is exited. In some cases, you may need to make your code portable with systems that don't have the Wait IE Ignore feature. In that case, you can just select between the two wait functions I have shown you. The code gets the WII bit. It checks to see if it is not set. If it is not, it calls the functions with interrupts disabled. If it is set, it calls the functions with interrupts enabled. For the portable part of the interrupt code, get and check the Wait IE Ignore feature, and if it is set, jump ahead and continue the interrupt function. If it is not set, then do the wait function check and the EPC correction if it is needed, as we covered previously. This ends the power management section.